Okay, guys, welcome. Today we're going to talk about the idea of proof by contradiction. Now, if a proof is difficult to do either directly, or we can't use induction, or we can't use something that's maybe straightforward, what we do is we do a proof by contradiction. Now, in order to prove by contradiction, we assume that what we want to prove is false. Then we show that this leads to some kind of nonsense, right? So we'll show that we were wrong to assume that the original statement was false, so then it was true, right? So I think the best way to see proof by contradiction is to look at some examples. Now, let's say that if a and b are both integers, then a squared minus 4b cannot equal 2, right? So if we want to prove this by contradiction, then we're going to assume the opposite, right? So what we have here is we have if something, then something. So if P, then Q. So we're going to assume that if P, then not Q, right? So that's how we would properly negate this, right? So in this case, we want to show, so we're going to assume that A and B are both integers, and we're also going to assume, I should say, if P and negative Q. And it's really assume P and negative Q. And then we show some kind of nonsense. Now, the opposite of this statement would be that a squared minus 4b is equal to 2. Okay, so we want to show that we're going to get some kind of a contradiction here, right? So I think the most standard way to do this is let's go ahead and let's solve for a. So we're going to get that a squared would equal to 2 plus 4b, right? Now, what we could do is we could take out a 2 out of this, right? So we get a squared is equal to 2 times 1 plus 2b. And this would show that a squared is even, right? Right, since it's divisible by 2. Now, if a squared is even, and we'll prove this later on, but if a squared is even, we get that a is also even. Right, so we get that a is even now. So if a is even, then a is equal to, say, 2k for some integer k. Okay, well, if a is even, let's go ahead and let's plug that in. So then we get a 2k squared minus 4b is equal to 2. And this would give us that 4k squared minus 4b is equal to 2. But then what we can now do is let's solve this for b. So we're going to get that, let's take out a 4 actually. So we'll get a 4k squared minus b is equal to 2. So then we get that k squared minus b is equal to 1/2. Right? And now we have a problem here, right? Because if you were to then solve this for b, you would get that b is equal to k squared. Let's see, b is equal to k squared minus 1/2. Right? But this is a contradiction, right? This is nonsense because k is an integer, and we're taking 1/2 from it, right? So k squared minus 1/2 is an integer minus a fraction, so this is going to give us a fraction. But b is also an integer from our assumption, right? So this is a contradiction, and sometimes we use the line with sort of an x through it, and this gives us, of course, the contradiction that we want. Right, so then this gives us that if a and b are integers, the original claim, then a squared minus 4b cannot equal 2, right? I think that's what it was. Yeah. Yep. And that's our contradiction. Now, one of the most famous proofs by contradiction is the proof that square root of 2 is irrational. All right, so we're going to assume the opposite. We're going to assume that square root of 2 is rational. Right, so we're going to assume that square root of 2 is equal to p over q. And we're also going to say that p over q is fully reduced. All right, just to make that clear here. All right, if we're looking at a rational number, we're just going to assume that it can be written uniquely as a fully reduced fraction. Okay, so, well, let's go ahead and let's take a look at this. If we have square root of 2 is equal to p over q, then one thing that we can do is we can multiply both sides by q. And we get square root of 2 times q is equal to p. Right? And if we square both sides of this, then we get that 2q squared is equal to p squared. Right? Well, this is sort of what we said in the last argument. We have p squared being written as 2 times something, so we're going to get that p squared is even here, which then implies, of course, that p is even. So then if p is even, p is 2 times k for some k. All right, well, now let's go back to what we had before. Well, then we have that square root of 2 is equal to 2k. I'm going to substitute that in for p over q. Right, now if I square both sides, I'm going to get 2 is equal to 4k squared over q squared. But then if I multiply both sides by q squared and divide by 2, I'm going to get that q squared is equal to 2k squared, which leads me to the fact that q squared is even, which then leads me to the fact that q is even. And this is our contradiction, because we have that p is even and q is even, but we said that this fraction p over q was fully reduced, right? So this is going to give us the contradiction. P over q is not fully reduced then, because we could divide by 2 if they're both even. So square root of 2 is irrational. All right, that's the idea. All right, now the last example that we'll do is we'll show that there are infinitely many primes. All right, so we will assume that there are finitely many primes. And we're going to assume that we have them all listed out, right? So we're going to say that our set P is a set of all prime numbers P1, P2, all the way up to Pn, right? Whatever n is, however many, whatever our finite list is, we're saying that it stops at n. All right, now we're going to consider the new number and I won't use P again here. Let's use something like, let's use K. All right, and we're going to take this new number K to be P1 times P2 times P3 all the way up to Pn. And then we're going to add 1 to it. All right, now a couple things to note here, really just one thing to note here, that K cannot be prime because it's not in our list. Right, because K does not belong to P, right? If K was in P, then of course it would be prime, but then it would already be in our product that's right here, right? Now what we're going to do is that since K cannot be prime, at least one prime number divides it. At least one prime number divides it. and we'll say that it's P sub j, right? Any one of those arbitrary things will divide Pj, right? So we're going to divide by P sub j, right? And we'll say that in our list, somewhere maybe over here is Pj, just so you can see that it's coming in there. Now, if I divide both sides by P sub j, I'm going to get that K over P sub j, right, should come out cleanly, and I'll get P1 times P2. And now I won't have j. I'll have Pj minus 1, and then I'll skip to j plus 1. And then Pn plus a 1 over Pj. All right, but of course, this is our contradiction, right? Because this should divide it cleanly, but this says that we have a remainder of 1. Right, so this is a contradiction. So then this leads us to conclude that there must be infinitely many primes. Okay, so that's the idea behind proof by contradiction. All right, so I hope you enjoyed, and I will see you next time.